Let us take some other example wherein I have an interesting point to discuss. See, in general, in E2 reaction, you need the groups to be removed in anti-periplanar geometry. That is at an angle of 180 degrees to each other. Look at this. Now, when this kind of a question is given, convert that into Newman projection. So from Fisher to Newman. Hope you all know how to convert. Come on. Phenyl, bromine and hydrogen. Right? Now, this one. Phenyl, actually no, we have to go for 2 steps. But logically, 1 second. No, but logically, this can be written. If you know the cut short method, we can actually take it here and this one here. Come on. Hydrogen here, then methyl here. Hope you know this logic. Or else you'll have one more step before getting this. Then that will be in eclipsed format with this phenyl group coming here. But you apply the logic, get it in no time. Now, see at this carbon, you got bromine here. That is a front carbon. Now, there is a hydrogen exactly at 180 degrees. That is with anti-periplanar geometry. At the second carbon or the rare carbon. So we have hydrogen and bromine, anti-periplanar to each other. This is very important. At an angle of 180 degrees. Now you just remove them. Okay. Bromine goes out. Even this hydrogen also in the form of H plus is abstracted by a base. Then what do we get? Come on. A C double bond C with the pH and hydrogen onto this side. CH3 and the pH onto this side. With the CH3 onto the side of pH. These two are onto the same side. You be very careful. Then this pH. Right? So we got a trans product. The car, TAM, TSM, I mean CSM, TSR kind of things can be applied even here also. We will see them once we go for the questions after the theory discussion. Now, in general, we follow anti-periplanar geometry in eliminating the groups in E2. But even here also there is an exception. Consider a bridged compound. A rigid one. These are the bridge heads. In case of bicyclic, which is a rigid structure, we follow thin periplanar geometry, thin coplanar, you can say, with an angle of 0 degrees. So this is bicyclic, is a rigid one, and here we follow thin coplanar geometry. The angle is 0. That means they must be thin to each other. Remove these two. Onto the same side. Now we get this. Okay. Now these two are actually anti to each other. But we take bromine along with this hydrogen, which are thin coplanar. It is because of the rigidness of the bicyclic compound. Okay. So this is all about E2 reaction. Now it's even CB. Elimination unimolecular conjugate base mechanism. Okay. Let us straight away go for the mechanism of E1CB reaction. Here again, like the E1, it also has two-step mechanism. But the steps are exactly opposite. Let me give you. Okay. See, in the first step, halogen. Now this is alpha carbon, and this of course is a beta carbon. Now here a base abstracts this H plus. Okay. As and when the H plus is abstracted, this bond comes to this carbon atom, which has got an electron withdrawing group attached. That is the interesting part about even Cb. Come on. You will get C minus. And this carbene ion is, of course, stabilized due to the presence of a strong electron withdrawing group. Yes. Base has gone off along with the hydrogen in the form of H. Now, suppose this is a species, this one is a species. When a H plus is removed, what do we get? We get the conjugate base of that. Conjugate base, which of course is a carbene ion in this case. This carbene ion is stabilized by a strong electron withdrawing group, right? Seen even abstraction of the proton by the base is the second step. Here it is the first step. I think you have noticed. Then, now the conjugate base or the carbene ion supported by the electron withdrawing group. Yes. This comes here. As and when it comes here, halogen is lost in the form of halide ion. Of course, the first step is slow or rate determining step, whereas the second step is fast. Here, of course, we get this, and here, in fact, you have the electron withdrawing. Okay. So in the first step, we get a conjugate base. That is the reason why it is called conjugate base mechanism. Okay. Now, let me give you an example. Base abstracts this H plus, then it comes to this carbon. Now this is the electron withdrawing group. Okay, what do we get? PH, H double bond O, then CH minus. Carbene ion is formed, then CH2 OPH. As and when this comes here, this one goes off. That is the leaving group here. I've taken a different leaving group. Now here the carbanion, of course, is stabilized by the electron withdrawing group. This is the electron withdrawing group. Now the final product that we get is this. Okay. So this is how even CB mechanism can be explained. Now let us go for some interesting things or the important points like kinetic isotopic effect. What do you mean by kinetic isotopic effect? It can simply be given as Kh by Kd. That is the rate or a rate constant when hydrogen isotope is used by the rate or rate constant when its heavier isotope, that is deuterium, is used. See, in this case, the bond that undergoes cleavage is CH. In this case, the bond that undergoes cleavage is CD. We know that the bond energy of CD bond is more when compared to CH bond, right? So this particular bond undergoes cleavage readily. Bond can be readily broken. Let us take the example. Now let us take this example. E2 reaction. Yes. Along with this bromine, this hydrogen is lost from this beta carbon, right? Then we get PH, CH, double bond CH. Let me call this KH. Similarly, if we consider the heavier isotope deuterium, we get, of course, bromine goes off, alpha, then this. So along with the bromine here, a deuterium is lost. So this involves cleavage of CH bond and this one involves the cleavage of CD bond. Come on, PH, CD, double bond, CH. Let me call this KD. Okay, this is what is actually called kinetic isotopic effect. Now we'll be comparing the rates by taking different isotopes. Okay, and this is of two types. primary, secondary. Primary kinetic isotopic effect, secondary kinetic isotopic effect. Let me also tell you that in E2 reactions, we have primary kinetic isotopic effect. That is again a very important point. Look at what is primary kinetic isotopic effect and what is secondary. Only one difference between primary kinetic and secondary kinetic isotopic. Let us consider the same example. In primary kinetic isotopic effect, it will be this. Kh by Kd will be greater than 2. In the previous E2 reaction, what we have taken, in general, E2 reactions follow primary kinetic isotopic effect. I'll tell you what this is. And in case of these reactions, Kh by Kd will of course be almost equal to 7. See the difference. But what is primary kinetic isotopic effect? See if the carbon hydrogen bond or the carbon deuterium bond undergoes cleavage in the rate determining step. In the rate determining step, then that is said to be following primary kinetic isotopic effect. In the rate determining step, yes, in E2, this is what happens. In the rate determining step itself, base abstracts the proton, this comes here, this one goes off. The cleavage of this carbon hydrogen bond occurs in the rate determining step itself. This is what is called primary kinetic isotopic effect. Involves the cleavage of carbon hydrogen bond in this case, if taken carbon deuterium bond. This is where we say that the primary kinetic isotopic effect is observed. Of course, we get this. So in E2 reactions, primary kinetic isotopic effect is followed. Then what is secondary kinetic isotopic effect? Secondary kinetic isotopic effect can be simply given as this. Kh by Kd will of course be less than 2. In primary it is greater than 2, here it is less than 2. Let me give you an example taking the SN1 reaction into consideration. SN1, nucleophilic substitution unimolecular, similar to our E1 with some basic differences. I have taken a tertiary alkyl halide I'm using a solvent water, which acts as a weaker nucleophile here. And in this case, you know the rate determining step is actually the breaking of this carbon-chlorine bond. This is the rate determining step where you get a carbocation. But we don't have any carbon-hydrogen bond in the rate determining step. We have a carbon-hydrogen bond in a bond that is adjacent to the bond undergoing cleavage. That is, you got carbon-hydrogen bond in the thing other than the bond that is undergoing cleavage. Okay, so here of course you get this. Now if suppose this is taken, it is again the same thing that happens. This is the rate determining step, but our carbon deuterium bond is not in the rate determining step, other than rate determining step. So then this is said to be secondary kinetic isotopic effect. Earlier in primary it was the carbon hydrogen bond undergoing cleavage in the rate determining step itself. And in this case it is not the same. It is in a step other than the rate determining step. Okay. So if carbon hydrogen bond undergoes cleavage in the rate determining step, that is primary, in all E2 you can see primary kinetic isotopic effect. Whereas in SN1 reactions, which are almost the same as similar to the E1 reactions, of course, if we know the SN1 and SN2, we can actually compare the two. In this case, the cleavage of the bond is not in the rate determining step. It is the step or the bond other than the bond that is undergoing cleavage in the rate determining step. This is secondary kinetic isotope. Now let me tell you one more. There is something called Brett's rule. I have just two examples, but very interesting. So this is a bicyclic compound. These are the bridgehead atoms. Let me take a chlorine here. Now let us give name to this compound. Numbering begins at one of the bridgehead atoms. Go via the longest first. Of course, here in all the bridges you have 2, 2, 2. So let us go this way because we have a substituent here to the next bridgehead, then again to the first bridgehead via the next longest. But here all three bridges are of equally long. Then 7th and 8th. Let us write the name of this. It is a 2-chloro bicyclo. First one has 2 carbons, second also has 2 carbons, even the third one also has 2 carbons. And a total of 8 carbons. This in fact has to be in the descending order, but because here all the bridges are of the same length, having the same number of carbon atoms, we have written it that way. And the interesting point to be noted here is, it is a non-zero bridge. Now in this case, if we go for a strong base, of course, there are 2 possibilities, right? So this is the alpha carbon, this is beta, even this also is beta. Let this be the possibility A and this be the possibility B. See, the product formed in A is this. In case of A, it will be this. This is where you get a double bond. Whereas possibility B gives this. Okay. Now, according to Brett's rule, remember, this is not possible. This, of course, is okay. But only thing is, it says that the double bond cannot be formed at the bridge head. This is the bridge head, right? The double bond cannot be formed here. If the largest ring is of less than 8 carbons, here no ring is having more than 2 carbons. So this is Brett's rule. You get 2 products, but this one is of course not possible. Let me say that according to Brett's rule, in a non-zero bridged bicyclic compound, double bond cannot be formed. Formed at bridge head, provided the largest ring is of less than 8 carbons. This is interesting. So, you cannot form the double bond at the bridge head. And the other case, let us take something with zero bridge. In that case, it is okay. See, these are the bridge heads, and this bridge has got no carbon atoms, so it is zero bridge. In this case, Let us consider alpha, beta, beta. Let this be the possibility A and this be the possibility B. Now in this case, A gives the major product. Very interesting. So here this is what you get. This is in fact the major product. Then going for B, this is minor. See major, and here the double bond is at the bridge head because it is zero bridge. Only when it is non-zero bridge and has the largest string having less than 8 carbons follow by X2. Major, though the double bond, the double bond is at bridge head. So this is the other interesting thing called bridge